Okay, so this is kind of a follow-up to the last lab that we did in the fall. If you remember that one, we had a cart was on the track. We had this disc, a thread, and we had a hanging mass here. And what we found was that the amount of force, friction force between the pulley and the thread was not sufficient enough, and what would happen is if the moment of inertia of the disc was large enough, you'd have slippage between the thread and the pulley. So when we didn't have the disc on there, we had pretty good agreement between the theoretical and the actual. But when we did the one where we had some moment of inertia, there was a difference. And the difference was because the thread was slipping. So what we're going to do here is we're going to have the disc again. We're going to have so there's the disc, and on the disc is a pulley, like that. And then down here we're going to have another pulley, and we're going to then thread the pulley, the thread, we're going to take the thread over this pulley. We're going to take the thread over here, over this pulley, and down like that. And we're going to have two hanging masses. So, no cart. And we're going to measure the acceleration of this system just like we did here. Now, there are two things that's going on here. One is that the difference in the mass of these two masses is what drives this thing. If these masses were the same, it would just sit there and nothing would happen. So that additional mass, that starting mass, where they're the same, provides tension so that there's less likelihood that this thread is going to slip relative to the pulley. The second pulley here is to get these apart. If I tried to do this all with just one pulley, they would run into each other. So this second pulley is we're assuming the moment of inertia of this pulley without a disc is negligible. It's connected to the same configuration as got one of those rotary motion sensors. So the other thing too is that by placing the second pulley below the first pulley, I increase the amount of wrap around the pulley. So that also makes it so that if I let it drop vertically, that would give me the maximum amount of wrap, but then they run into each other. So these are fairly close to each other. So it's not a complete 180-degree wrap, but it is more than if I went out horizontally and then down. So that's why it's displaced vertically some amount. And they're, like I said, the closer these two are to each other, the more wrap you have, the closer they are, the more likely they're to run into each other. So it's kind of a compromise situation. Now, as far as the theoretical calculation, it's very similar to what we had before. Is you're going to calculate the acceleration, the linear acceleration of these two masses. And remember, force equals mass times acceleration, or acceleration equals force divided by mass. So this is the inertia part, and this is the force part. So in the numerator, we need forces. And the forces that are acting here are the forces due to the weights of the two objects. The inertia of the disc doesn't cause this thing to, if I have these two masses the same, this is not going to turn. It doesn't, all the disc does is contribute to slowing things down. So in the numerator, what we have is, let's call this 1, call this 2. So you're going to have, let's assume, so we're going to have m1 times g. That's going to be the weight of this first object. and then you'll have M2 times G. Now, depending upon which, the sign is not that important. The important thing is these two masses are different, and that's going to cause this thing to move. So that's the force part. It causes things to happen. And then you've got three inertias. You've got M1 plus M2. And then you've got the inertia associated with this disk. So what we do is we take the inertia for the disk and we divide by the radius of the pulley squared. So you have to convert this moment of inertia of the disk into more like a linear term. And we calculated this last time. We'll just give you that number. That's the moment of inertia of the disk, which of course is 1/2 the mass of the disk times the radius of the disk squared. But in terms of this, how much the moment of inertia of the disk affects this system, it's the radius of the pulley that's important, and not the radius of the disk. So that's the equation. That's the theoretical equation that we'll use to calculate the linear acceleration of these. There's also an equivalent alpha expression, which would look something like this. They're equivalent to each other. But you'd have M1R radius of the pulley squared plus M2 radius of the pulley squared plus the inertia of the disk. So this is kind of comes from torque equals I times alpha. So if you solve for alpha, it's going to be torque divided by the moment of inertia. So this is the torque. It's caused by these two tensions on either side of the pulley. And those difference in tensions are caused by these two masses. And then the moment of inertia of the disk is by itself, but then you have to convert these masses here into equivalent moment of inertia type terms. So if you took this and multiplied and divided by r, take the numerator and multiplied and divided by r sub p squared, you'd get this. Or actually, if you took this one, the numerator and denominator and divided by r sub p squared, you get that. And if you multiplied these two terms by r sub p and multiplied this by r sub p, you would get this expression. So anyway, I think we're going to measure linear acceleration. So this will be the theoretical formula. And what we'll do is we'll measure the acceleration of these objects by using the software. And of course, as we've done in the past, what we'll measure is velocity versus time. And we'll take the slope of that curve. And the slope is equal to A. Okay. So that is the idea of what we're doing today. And we are going to look at all three pulley sizes. What will happen is the larger pulley will probably see very little slippage, and we'll see good agreement between the theoretical and the actual. When we go to the smaller pulley, what happens is there's less area over which to spread that force, and it's more likely to slip. So we're going to do a large pulley, a medium pulley, and a small pulley. And we'll find the small pulley still has slippage, but the big pulley doesn't have slippage, or has very little slippage. That's the hope, at least.